All right, guys, here's a buoyancy example problem. A hot air balloon has a volume of 2,300 cubic meters. The balloon fabric, the envelope, weighs 900 newtons. The basket with gear and full propane tanks weighs 1,700 newtons. If the balloon can barely lift an additional 3,200 newtons of passengers, breakfast, and champagne when the outside air density is 1.23 kilograms per cubic meter, what is the average density of the heated gases inside the envelope? All right, so I think it's best to start with a free body diagram here. And for a hot air balloon, we only have one upward force, which is going to be the buoyancy force. And as discussed in the video, by Archimedes' principle, this is the weight equal to the weight of the displaced fluid. That's the volume, or that's the magnitude of the buoyant force, it's equal to the magnitude of the weight of the displaced fluid. And we have a lot of down forces here, right? We've got the balloon fabric, which was 900 newtons. We have the propane tanks, which was 1,700 newtons. And we have all of the passengers, which was 3,200 newtons. And the problem asks, okay, when is this barely going to give liftoff here? Meaning, when is the buoyancy force equal to all of these other forces so that we're just at the cusp? Any more buoyant force and we're going to go up, or any less mass that it's trying to pull up and we will float. So we're going to find out when the buoyant force is equal to the sum of all of these guys down here. So, and we have one other factor to consider. And that is the mass of the gas inside the balloon itself. So we also have the weight of the gas, which will do mass of the gas times g, one extra downward force. So lots of pieces here. We have all of the components listed, which was the balloon itself, the basket, the passengers, the propane tanks, and the gear. And we also have, let me just go ahead and draw a picture. We have our balloon with its basket here. And we have the weight of the balloon itself and the basket and all the gear and the people in the gear. But this is also a large volume of air, which is also going to have its own gravitational force, which points down. So all of these components, we're looking for the point at which the buoyant force, which points up, balances all of those out. And the buoyant force, we said, is equal to the weight of the displaced fluid. So the magnitude of this buoyant force is. So let's figure out what the magnitude of the buoyant force is going to be. And it's going to be equal to the mass of the displaced fluid times g, which is going to be equal to the density of the displaced fluid times the volume of the displaced fluid times g. And we also have this weight of the air here, which we only have in symbolic terms. So we can rewrite this term. We have the mass of the gas times g, and that's going to be equal to the density of the gas, which is what we're solving for in this problem. It asks what the density of the gas is, times the volume of the gas times g. Now, in this case, since the balloon is fully submerged in the air, we have the volume of the fluid is equal, or the volume of the displaced fluid is equal to the volume of the gas inside the balloon. These volumes are equal, so we're just going to call this volume V. And now we're in a position to write down the sum of our forces in the y direction. The up force is just going to be the buoyancy force, which is the density of the fluid times the volume times g. Okay, we're going to have minus, let's add all of these together. We have 900 plus 1,700, which is 2,600, plus 3,200, which is a total of 5,800 newtons. We're going to have minus 5,800 newtons. Then we have minus the mass of the gas itself inside of the balloon times g, which is going to be minus the density of the gas times the volume times g. And we want to know when these forces sum to zero, meaning they completely balance one another. That's the critical point. Now we're looking to find the density of the gas. So at this point, we just need to do some substitution here, or some rearranging. And we'll move this term to the right-hand side. So we get the density of the gas times the volume times g is equal to the density of the fluid times the volume times g minus 5,800 newtons. or the density of the gas, is equal to the density of the fluid minus 5,800 newtons divided by the volume of the balloon times G, or the density of the gas is equal to 1.23 kilograms per cubic meter minus 5,800 newtons divided by the volume of the balloon, which was 2,300 cubic meters, times G, which was 9.8 meters per second squared. Plugging that all into your calculator, we get that the density of the heated gas is 0.96 kilograms per cubic meter.